I'm going to go through a video of how to write an equation of a rational function when you're given a graph. So for instance, if we were given this graph here, we sort of scan this, and the first thing that I notice is that I have some asymptotes. So you're going to estimate and just draw some lines here where those asymptotes occur. All right, so we're just really going backwards from when we were given a general form. We're looking at the attributes, and then we're going to translate that into this general form of a rational function, which is a polynomial in the numerator and a polynomial in the denominator. And then we also have this stretch factor a, and we're going to solve for that just the same way we did with when we had a straight up polynomial function. Okay, but anyway, so I have an asymptote at x equals -2, and I have an asymptote at x equals +2. Sorry, this is x equals -1 here. Okay, -1. So these tell me that x cannot equal -1 and x cannot equal 2. That means that my domain excludes those values because x can never equal those numbers, okay? So if I were to write my domain here, and then I'm going to scan here, I see my function continues on this way and continues on this way. So I could write my domain as -∞ to -1. Okay, that's this stretch here. And then I can't equal -1. Now I got to pick this stretch up here, -1 to +2. Right? I can't have x equal 2 because it gets close, close, close. My function is plunging down there. And then it picks back up here at 2 and keeps going to infinity. So I've got -∞ up till -1. This bit here is -1 to 2. And this little bit here goes from 2 to infinity. All right, so if I know that I have vertical asymptotes, those become, in factored form, those become where my denominator would equal 0 if I plug those in. All right, we'll talk about the powers in a second. All right, we know that our numerator represents where I have intercepts, right? So where q of x, the denominator equals 0, I have vertical asymptotes and or holes. Where my numerator equals 0, I have x intercepts. Okay, so if I look at my graph here, I have an intercept here, and I have an intercept here. So at the point -2, 0, and at the point 3, 0. So that means that I would write in factored form when x equals -2 and when x equals +3 here, that would make my numerator 0. How do I know what power I'm going to use? Well, I'm going to use that multiplicity rule, right? So if it kind of looks like a linear, right, straight up through the axis, it crosses it, means I have multiplicity 1, all right? In the denominator, in factored form, remember we talked about last class, if I go in opposite directions, all right, around -1, if it looks like 1 over x, then I have to the first power. If it looks like 1 over x squared, where they both go to the same direction, that would make my power to the second power, okay? So if they go in opposite directions, I have multiplicity 1. If they go in the same direction, I have squared, okay? So that's how I figure out the exponents. So now, how do I figure out that a value? Well, just like I did with polynomials, I'm going to find a point on the curve. Usually, if you can find a nice, neat point, the y-intercept, right? X equals 0, y equals -2, right here. I can plug that in now to my f of x function. So I have f of x equals a, x plus 2, x minus 3, over x plus 1, x minus 2. So I'm squared. So I'm just going to plug 0 in. F of 0 has to equal -2, right? So if I plug 0 in for all those x values, x equals 0, x equals 0, x equals 0, x equals 0. Now I can solve for a. When I evaluate this, I get -6 over 4 times a equals -2 here. And then I simplify and I get 4/3. That's how you can come up with the equation for a rational function if you're given the graph.